All right. All of the other distributions that I did, the binomial and the Poisson distribution, are for specific distributions. The most important one, in my opinion, which I think is used the most, is the normal or Gaussian distribution. This is used for continuous random variables. And the equation is kind of nasty. I'm going to plot it first. I'm sure you've seen it before. Maybe you haven't, I guess. You're watching this on YouTube. But it looks like this, and it can be flatter. It can be narrower and taller. It all depends on the standard deviation of the distribution, okay? The equation for this is f of x. This is x, obviously. This here is the mean, right? So the mean is somewhere on the x-axis, okay? It is equal to 1 over sigma square root of 2 pi e to the minus, I'm gonna make sure I don't mess this up, x minus mu squared all over 2 sigma squared, okay? That's a really nasty equation. If you plotted that in Python, like it'd be a really smooth curve. Some interesting properties about this though is that if you integrate from minus infinity to infinity f of x dx, you're gonna get 1. And what that means is that basically that the probability from, it's a continuous random variable, okay? So it can be any value from minus infinity or positive infinity. And basically it means if I take all of the possibilities from the left half to the real line all the way to the right, and I integrate it, and I find the area under the curve, I'm going to get 1. Full probability. What that means though is that if the standard deviation shrinks, the curve has to get taller, right? Because the area is conserved. And so if it flattens out, it's essentially saying that the standard deviation is getting wider, okay? Let's see, what other interesting properties do I want to talk about? There is something called the z-table, which is a better way to represent the distribution. It's basically a change of variables. And what they do is they say, let z equal x minus mu over sigma. And the reason why they do that is because they basically, mu and sigma are constants. Mu is the mean, sigma is the standard deviation. And so z tells you the deviation from the mean, right? So x is, let me see if I can write this notation correctly. X is in the set of, how do I want to say this? Let me look at it over here. The center of this curve, I drew this right here on the y-axis, but the center of this curve is actually at mu. It's actually at the standard deviation. So if the at the mean. So if the mean of my distribution was 15, my curve would be shifted all the way over to the right. But the nice thing about this change of variables with z is that because you subtract off the mean, it means that the center of the curve is actually at 0. So the mean of this distribution is actually 0. And what that means is that f of z turns into 1 over square root of 2 pi e to the minus z squared over 2. And if you notice, sigma is 1. So the reason why they do this change of variables is because A, the equation for the distribution is way easier. And the other thing is that you can use the z distribution for any distribution under the sun. Because as long as you know the mean and standard deviation of your normal Gaussian distribution, you can do a change of variables and change it to the z domain. And then now you've got a distribution that has a mean of 0, a standard deviation of 1, so the figure always looks the same. It basically takes every single distribution out there, every normal distribution out there, and changes it to a change of variables there. Okay? The other thing that's neat about this is that there is a z distribution here that tells you, so if I plot and this is being centered at 0, right? So this is z now, and this is x. Sorry, yeah, this is x. This is the x-axis. It's centered at mu. This is the z-axis. It's centered at 0 now. What if I want to find this area here, right? If I wanted to do this area for this here, I would have to integrate this curve, and if I change the mean of the standard deviation, it would completely change. But because the z distribution is always the same, the area under this curve, AZ, is the integral from 0 to, what do they call this here? So they actually put z right here. Is the integral from 0 to z of f of z dz. And since f of z never changes, I can create a table that has all of this in here. And so I'm going to hold this up to the book. Let's see, I probably need to focus. There we go. So this is a z table that's in this instrumentation book. And basically it shows everything in here. So if I give an exam, I'm going to have this table on here. And then if you're doing a homework problem, you can refer to this z table in the problem there. Okay? So I think at this point it's probably a good idea to do an example with the z table. So I'm gonna pause here. This is basically all I want you to know about distributions. There are some other distributions called the standard log normal distribution and the exponential distribution, but actually I'll probably do the exponential distribution. So I'm going to do an example on this, the normal Gaussian distribution, and I'm going to do the exponential, and that'll probably be it for this section. Okay? All right, I hope you enjoyed this lecture. Time to move on.